Hello, party people. It is Will Pemble. I have today with me super magnet man George Mizzell. George is a freaking genius, man. If you want to know anything about anything you could do with magnets, George is the guy to talk to. And since we're talking about building a launch coaster in the backyard, and the idea is to make it launch with magnets and to make it stop with magnets, there's nobody better to talk to than George. George, my brother, I'm so glad you're here.
Thank you. Thank you. Enjoyed being here. I'm looking forward to it. And it's already got me thinking on some other videos that I want to do with electromagnetic launching that have sort of been ideas I've had for a while. Everything from launching rockets magnetically to I've worked with people on zip lines and other things for stopping them. So I think the things that I've worked on in the past we're going to be able to use with your project and get that roller coaster going.
Oh my God, I'm so excited about this. Yeah, so like I've got a million questions. Like I'm in the garage. I tend to wander around, as you may have noticed.
I can
But
tell. It looks great.
I'm in the garage right now, and so what I've got so far of the coaster is just that. That is the only thing. That's a 20-foot long piece of 24-inch gauge track that John and I built, I think, back in part 2 of the Backyard Launch roller coaster series. This is, I think, part 5 by now. But anyway, so we built that one piece of track just because we wanted to get an idea of, John and I, John and I are both like adults, right? And so the last track we built had 18-inch gauge track. So this one is 24. We figure we can get a little bit more stability if we're doing hardware and stuff to push. We got a little bit more room, and frankly, it's just like a lot more comfortable with somebody who's got a butt as big as mine. So that's that's like the last reason is actually the first reason we did it this way. But so that's what we got so far, and I can take you out. We can run out to the backyard where the coaster's gonna be. Oh, did you hear that? That was you banging against the wall. All right, hang on.
Have you torn down the existing one? I heard on one of your videos you're tearing that one down and going to build a new one.
So here's the thing that not a lot of people know, but I guess since you asked, we should go ahead and spill the beans on it. Yeah, the existing one. Hang on, I'm putting up my little sun shield. This is how it goes around here, George. So we got like. Let's see. Just cranking up the.
There you go.
All right. Okay. So.
Let's see. I watched the TV show. About mega mansions and everything, and I've been looking, and I haven't seen one yet that's got a roller coaster in their backyard. So they haven't done your house yet.
No. Well, they haven't, and again, this is like nobody knows this yet. They haven't done one yet, and they won't, because one of the things that happened along the way was we ended up with a boatload of sort of foundation geology issues and problems in that big house, in the big awesome house where the Gold Boss roller coaster was built. What happened was we started at first, and it's like a ridiculously minute story, I guess. But anyway, I might. But we noticed, like in the first level of the house, it was kind of built on a hillside, big 6,000 square foot house, beautiful place. We noticed that the floorboards in the basement or in the lower level where the kids' rooms were just starting to spread a little bit. I was like, well, that's weird.
That's not
and then we noticed that in the driveway, the pavers on the driveway were just starting to spread a little bit, and a couple of other things. Long story short, the soil where we live is it gets like really crunchy when it's dry, and then when it rains, it gets really sloppy and muddy, and that over the course of years and drought and everything like that. To make a short story tedious, which I feel like I've done already, we ended up with about $1.4 million worth of foundation and geology work that needed to be done. And we thought, yeah, right? Now I don't know what it's like in Alabama, but here in the San Francisco Bay Area, 1.4 million, that's a lot of money.
That
And
is.
yeah, so we decided maybe the better part of valor was to declare victory and depart the field. So the Gold Boss coaster is no more. It's
Oh,
torn down, and yeah, it's gone. And now we made that
mm-hmm.
decision. We made that decision about the same time we made the Gold Boss. We updated the periodic table of roller coasters, and I'll get you
Mm-hmm.
a shirt. But we made
Yeah.
the Gold Boss coaster. I think it was number 118 because that's one of the unstable elements, right?
More unstable.
In chemistry. And so, you can do it, but it doesn't last long. And so we proved that
Mm-hmm.
that element could be built. But
Those
so
fast.
Gold Boss is gone. And then we, and so like here's like the normal backyard, the new backyard, and it's just normal.
Yeah.
There used to be a swimming pool here. There's not anymore because drought and ecology and such. But so anyway, no more Gold Boss. It's gone. I've got a little bit of footage of dropping it off at the recycling place. I got almost.
Tears were shed.
It was sad, dude. But it's not all bad because I got almost $145 for that steel when I brought it to the recycling
wow!
place.
All right.
So it wasn't like a total loss. I made some serious money. I like
you turned $10,000 into $145 in that.
I did, and you're not the first person to point that out. So
yeah,
you know what I mean.
my wife was really good with that with yard sales years ago, and she could turn $20,000 worth of stuff she's bought into a $1,200 victory on a Saturday and be really tickled about it.
Yep. So here's one of the remaining. Let me get out in the light here. Here's one of the remaining chunks of of the Gold Boss.
I remember that.
That's the front wheel assembly. I made a video the other day. I want to get a little metal mill and start to make awesome bits and pieces instead of the monkey stuff that I've been up to lately. But anyway, so now you've seen kind of like a couple of the bits and pieces. I'm going to stop talking because we're not here to talk to me. We're here to talk to you. And so what do we do if you look down just like over my shoulder there, right where that avocado tree is that Liz grew from a avocado seed, starting right about there, that's going to be like or ending right about there, that's going to be like our 20 foot. So like from here over to there, we've got like 20-ish feet of space. And my hope is that we can go from zero on a level piece of track, we can go from 0 to like 21, 22 miles an hour. And I think that'll be enough to get us up to the top of a 15-foot high hat.
Yeah.
That's the goal, is to kind of see if we can make that come true. And I think it's safe to say, George, that that's all I know about it.
Pardon? Are you going to make this roller coaster go on top of the house?
No. We're going to keep this one. We're going to keep this one pretty simple. It's going to go out and up. So it's going to go straight out. Think like, are you familiar with King to Ka at Six Flags Great Adventure in New Jersey, or Top Thrill Dragster?
I've been to one of those.
Yeah. Okay. So the party people listening to this video or watching this video, they'll know what I'm talking about. And so King to Ka, basically it goes, or Top Thrill Dragster, maybe a better example. It goes straight out and it launches. Top Thrill Dragster goes from like 0 to I think 120 miles an hour. I mean, it's like fast.
That's pretty rocket fast. There.
Yeah, in a few seconds, in less than 3 seconds. It's crazy. Straight out, and then what I'm thinking is probably like I want to say like a 9-meter radius slope, which I think gets us to like right about 4 Gs.
Tight turn.
Yeah, pretty tight turn. Then you go straight up, and then over a top hat, and then down and straight back. And so from the beginning of the launch to the end is about to the beginning of the climb is about 90 feet. And so straight up, over, back and then loop around. And so it's a pretty tight, you can see it's a pretty small yard. We don't have a whole lot of space to work with back in here. And so we're going to we want to keep it pretty darn tight.
Well, and I've been thinking about this since you and I talked about this last week. And what I'm picturing is something that the launch mechanism would be driving a cylinder that would push it. Because keep in mind, you're not starting, you are starting with an inertial mass of 200 pounds, say. And if you're pushing that, but you're not pushing it against friction on the ground. It's not like you're going to keep your feet on the ground. So you've got rolling friction is very, very low on that cart. So you may not need 30 or 40 pounds worth of total thrust to move it at the speed you want to. So you'd figure it from that standpoint. But I'm picturing it if underneath your cart, you've got the cart that rolls like this, and if we have a rod underneath it, and you just have a plate on the end that it's going to push against, when you accelerate it with the electromagnetic plunger, it's just going to hit it like this and push the cart. Now the cart goes. And then you'd just be able to retract the coil back with this and be ready to go for the next time. Or if it's going to come back to the same place, that could be your braking system so that it comes back, and as it goes, it's dissipating the energy back through the coils. But all you'd need is a series of coils. And the way we do this is you'd have a series of coils that, let's just say, 2,000 turns, number 24 gauge wire, something like that. And we're going to hit it with a capacitor bank. So you put several capacitors that you charge up. So you get a big energy pulse. And you start with different levels. You just want to get it moving first. And then 6 inches later, the second coil hits. And then 6 inches later, the third coil hits. So it's just sequencing the coils instead of trying to make one super huge coil that just kicks it out to begin with. You've got one that's going to accelerate. That way, somebody sitting in it is not going to get their neck snapped when they take off. They're going to feel it go, whoa, kind of like a Tesla 3 acceleration.
And it's funny. It's funny you should mention a Tesla 3 because I drive that car. It's one of my favorites. Have you ever driven a Tesla 3?
I have the Performance 3 as well.
Hey, me too.
What's better? And we just got the performance increase, and now it
dude, was that awesome?
It rearranges your face when you take off. I said, I mentioned, I tweeted to Elon that I've got a new facial exercise to help try and pull the wrinkles out. I just accelerate more frequently in the Tesla Model 3, and it's helping to stretch the wrinkles out.
Dude, that was so awesome. I like, you and I have been around a while. I've never had a car before where they retroactively improve the car. We got in California, you can get Tesla insurance. And so basically they retroactively reduced the price of my car because Tesla insurance is half as much. All right, we could go on about Tesla forever and ever. So wait a minute, let's go back to these coils. And so a couple of quick closed-end questions, clarifying questions. How many do we build these coils ourselves, or do we purchase them?
I generally wind them myself. It's not a hard thing to do.
Sounds like fun.
It is. It's really boring. You sit there and you count up to 100. You make a tick mark on the board. You count to 100 again. You make a tick mark on the board till you get to.
Do you have to, like? I'm thinking of like sewing machines, and when you spool up the little bobbin that goes underneath the needle in a sewing machine, you kind of want that to be pretty smooth so that it feeds out. Do you need your coil to be just exactly perfect?
A drill press is a really good tool to use. If you have a handy drill press, I use my laser cutter and made myself a mold for it so that I could always make them the same size. And then you can just turn on the drill press. And in the video I just released today, I show you my tachometer that I put on my drill press using a Hall sensor. And knowing that the drill is turning at 660 RPM, then I can start a timer. And if I want 2,000 turns, I know that I just have 2,000 divided by 666. And I just sit there and move the wire up and down, up and down. And in 3 minutes time, I've got a 2,000 turn coil.
Awesome. Next question. What is the diameter of I'll call it sort of like the spool that you
want the coil to be about the same width as the magnet length, which is going to be dependent on the power that you want. So let's just think in terms of 2-inch diameter, 2-inch thick N50 magnet, or two 2x1s that are put together. And you're putting that That's giving you a lot of magnetic thrust. Well, so a 2-inch wide coil is as much as you want. And if you looked at the latest video, you'll see that I show how much the field drops off as you get away from the surface. So to get to maximum power, I would look at using something that's a thin-walled stainless steel pipe. You're not really needing the structural strength. You just need something to hold the coils out and something for the magnet to move in the middle of. So
okay, how thin is thin? 14 gauge, 18 gauge?
Something like that. I've looked and found some online, the stuff that's got like 0.5 millimeter wall thickness goes well.
Okay.
A 0.5 millimeter,
right.
something in that 0.5 millimeter wall thickness range is going to be good enough to stand up to it, and stainless is pretty rugged. But what you're trying to do is take advantage of the magnetic field. In that set of coils that I'm using, PVC pipe that's about 1/4 of an inch wall thickness, or a little bit more than 1/4 of an inch, and from the surface of the magnet to the outside of the PVC pipe, I'm dropping something like 80%, 70 to 80% of my total magnetic flux. So it's like I've lost the whole bunch of that I can do, because it depends on the lines of flux that's cutting it. And so if the
does it go by the square of the distance? Is that kind of how that decreases
that is a
the
rough
magnetic force?
approximation. It doesn't hold, it's not a hard and fast rule, because if you take a large thin magnet, let's just say you took one that was 2 inches in diameter and 1/8 of an inch thick, the field is very weak on the surface, and it is going to drop much faster than you find with the inverse square law. If you take a 2-inch by 2-inch magnet, it drops pretty close to the inverse square law. And if you go longer, then it's not really changing that much. To go longer doesn't help a lot.
Okay, how many coils? All right, so far, I love that we get to build these things, because you know that like takes me all the way back to Mr. Wachtel's 4-H club when I was 9. So awesome! This is fantastic. We get to build our own coils. How many coils do we build?
I would say 3 or 4. And because what's going to happen is the velocity is going to be so high that the distance between the 3rd and the 4th coil is going to be longer than you really want it to be for your launcher. You really want to focus on getting the launch mechanism so that it's, let's say, in a 2-foot stroke or a 3-foot stroke, you want to be completely through accelerating. I mean, you want that to be through, because there's 2 things to keep in mind. One is, once the cart starts rolling, it's going to take less and less energy to keep moving it, and the plunger is going to run out of, it's not going to be making contact with it, because the coaster is already running away from it. And that initial impact, and that's one of the things we'll have to look at, is the initial impact. If it doesn't start by pushing, if it bumps if it's like a 1 inch away from it, and it's going to kick it away, and then as the plunger will travel about 18 inches and then make contact with it again, but now the plunger's going so fast, it's going to give you a secondary kick in it.
Right. Okay. So we're going to want to, I'm just moving closer to my
your Wi-Fi
spot here. Yeah, I'm moving closer to Wi-Fi. So we're going to want to, you know what you could do is on the end of the plunger, you could just put a neo magnet on the end of the plunger that would just like hold it to the cart. And that way you manage that, because if it, it could turn into like, a bullet. You don't want to like.
So you could also put a 2 or 3 degree incline, so you're pushing up, so the cart isn't able to.
The cart rolls back a little bit. Okay, tell me a little bit about you mentioned capacitors, right? Because one of the things that I've gotten, one of the comments that we've gotten a lot on the thing is I'm talking about when we talk about, LIM, LSM, those kinds of things, we're getting, the folks on the Coaster Dad channel, what they look at and talk about a lot is like real coasters, and they've got these giant big magnets and huge amounts of electricity and water or air to cool things. And I've got, 200 amps phase 1, which we can kind of turn into phase 3 if we need to, but huge amounts of on-demand electricity is not really available. I mean, we could do it, but you said something that was really cool a minute ago. How do we solve that?
Well, you use the capacitor bank, because the capacitor bank is like a bucket for electricity, and it just stores electricity. It just fills it up, fills it up, fills it up. And when it gets full and you close the switch, it dumps it all at one time. And it gives this really cool curve where it goes up like this, then it dumps it dramatically in that and creates that capacitor discharge curve. So you're
Okay.
dumping all of the energy at that one instant that you stored up. Let's just say you stored it up over 10 seconds, you dump it all in a tenth of a second. And so it gets that huge surge of power. And that's what really gives you the force you're wanting to see. Now, what we
Okay.
would look at is different size capacitors for each of the different banks, because like we're talking about, to me, if I'm riding
Now,
on the
when
road,
you say bank, do you mean the coil?
well, the bank is the number of capacitors it takes to deliver the energy that you want. You call them a bank of capacitors because you may need 4, 6, 8 of the capacitors together to create the total amount of energy storage you want to deliver in that pulse. And it depends on what energy we're wanting to draw and how much the coils can handle. The coils are going to be limited. First of all, you'll want to use, as I'm thinking through this, we'll probably use something like a 14 gauge wire. 14 gauge wire has low resistance. It also,
And that's for our coil.
Yes, that's for the coil. But what you have to look at is when you start trying to squeeze that much energy through a small wire, it creates a lot of heat because the resistance is very high. So you want the wire to be fairly large. The problem with the larger wire you go, and as I point this out in that wave energy video, the larger the wire is, the more coils, the more space the coils take up, so you can't get as many turns in. You may only get 200 turns of number 14 gauge in the same space, the same volume. You can get 2,000 turns of number 24. But
right, because you originally were talking about 24 gauge. Now, just so we're clear, and again, forgive me for like knowing so incredibly little about this. A piece of 14 gauge steel is, I don't know, about that thick, right? Like the wall, like the tubing we're using to build our coaster, it's 14 gauge tubing because it's light enough to where we can work with it. It's heavy enough to where it's strong. It's thick enough to where you can weld it successfully. Is that the same thickness of wire we're talking about, or is it measured totally different?
Wire is going to be very thin wire. It is 28 gauges, or like, let me say, the higher the gauge number, the thinner the wire gets.
Right.
And down to where, they make some that's 40 gauge. I've got some 40 gauge wire that's thinner than my hair. And of course, my hair is thinning out a lot more than it used to. So.
Yeah, I think I got about 40 gauge hair by now.
Yeah, that's about it. It's just very wispy fine as the wire is. And so the smaller the diameter, the greater the resistance. And it goes up by the square of the area. So the larger you make the wire, the lower the resistance and the more energy you can put through it in a pulse, because you don't run into it. It's like trying to take a gallon jug of water and force it through a straw in a second. And you just can't, it just can't handle it. And so what it does is it manifests itself in heat. And that'll cause your insulation to break down. That means you got to have fan cooling and stuff like that. But if you go with the larger coil, the larger wire, you don't get the benefit. You have to really work on your balancing act between, I need the wire to be as big as possible, but I also need a lot of turns, because 400 turns of wire is going to get you about 80% more power out than 200 turns of wire. But it's got a higher resistance, and it's a trading balancing act.
Okay.
You have to.
And if your coils get wider, like, so how long? So let's say we've got 14 gauge wire, 400 turns. Is that what we're talking about? 14 gauge wire, 400 turns. What's the diameter of our spool? Did we say about 1.5 inches?
Yes, the magnet would be, just say the magnet was 2 inches diameter, 2 inches thick. You'd have 2-inch pipe. And so as that coil goes out and you get a 1/2 inch to 2 inches away, then you're taking advantage of, you're only getting to work with 20 to 30% of your magnetic flux you had at the surface.
Okay. So the thicker and that's the distance from the center of your coil.
Yes.
So the thicker the wire, the more turns, the more energy you can move through it, but the more dissipation of that energy happens the farther you get away from the coil. And so so that's an amazingly.
Yeah. What you look at is the outermost half of your coil. If you think about it, just due to the fact that the diameter is bigger, you're putting a lot more wire in that outer half, and it's only giving you 20 or 30% of the work because you've lost so much of the magnetic flux. So it's a design issue always to find out how big can I make the coils and take advantage of my magnetism. And I look at it from a cost standpoint. if you look at things from a cost standpoint, that helps you in engineering balance more than anything else.
Yes, and in your marriage.
Yeah, if I look at the outer part of the coil and I think, okay, well, since it's bigger in diameter, I've put more wire into it. It cost me in terms of wire 125 or 150% of what I paid for the innermost coil. Yes, I got another 30% of power, but where is the trade-off? Is the 30% of power worth the 150% more increase in cost? And if you're sending somebody to the moon and you want to make sure you don't run out of power, then yes, it is. But if you are, if you're doing something and you want to try and balance the economics of putting the money in the system, that's why I was saying we would sequence the coils. You would have 3 coils here instead of 1 giant coil, because a giant coil, the outer half of what you're going to pay for isn't going to be doing you very much good.
Okay. Now, okay, so you've got like we've got 3 or 4 coils in a row. We want sort of continuous push, right? And so we want the second coil to actually be pushing a little bit harder than the first one, the third one to be pushing a little bit harder. So just like if you stomp on the gas in your Tesla, for the first 3 seconds, you're being pushed harder and harder back into the seat. It manages that acceleration beautifully. And so we want to do that there. How do we manage the timing? So like the first coil, the first capacitors dump, and that starts the whole thing off, right? And so that's easy to time, right? It's when you push the button. The second one, do we use like Hall sensors, or are we going to have to do the math? Talk to me about the timing of the subsequent coils.
You have several options. One is you could have a hole drilled in the side and just shoot an optical sensor across. All right, let's just say that we determine that with the speed, it's moving through the pipe, and here's the second coil, and when it gets to here, we want to be closing the switch, because by the time we close the switch, it's going to be right here, and we want to kick it from that point. You don't want to kick it early. If you turn on this coil just a fraction of a second early, it's going to generate a field that repels this end of the magnet.
Push you back, right?
And push it backwards. So you have to get this timing, and so you may want to just use a little optical sensor where you just have a little LED laser shooting across there, and as soon as it breaks the beam, it closes the circuit on the other side and says, now start firing the next coil. And that coil fires, and then you sense the next one. You have 2 options. One is you can really play havoc trying to do the balancing act on timing, and the slightest change affects your timing. But if you have a sensor, it doesn't fire until it gets to exactly where you want it to go, and then it fires exactly when you need it to fire, and that's what you want to be looking for.
Okay, cool. That's what I was hoping for. I've been thinking about, like, Hall sensors, kind of like, kind of beefy Hall sensors, but optical sensor just makes so much, it's just like so elegant and simple, just, light beam, right? Easy peasy.
Light beam across there. Lasers are $1 a piece, and the sensor that detects on the other side is just a couple of dollars.
Okay. Now I got an important question for you, and I'm really hoping the answer to this question is yes, because I'm a fan. Can we build the control system for this with Arduino?
And I'm not familiar as much with that Arduino as I'd like to be.
It's just a microcontroller. It's like a Raspberry Pi or a...
Yeah, you can use those, but here's the thing that you run into, and this is where power is such an issue. When you start to move a lot of power and you're going to dump it, 2 things happen. As the contacts close together, you're going to have an arcing to take place. And this arc bridges the gap while it's in the process of closing, and it burns away the contact points. Okay, so they have all different kinds of devices for that. But when you're doing it with microprocessors can't handle the load that you would be moving, but a relay can. So what you do is you use the microprocessor to control the relays, and the relays control the contacts.
That's what I was talking to. And then we got a comment. I mentioned that in like the last video we were talking about, like little Arduino, it's a little 5-volt thing, right? I mean, you can't, that's nothing.
Yeah, you can take a processor that size, the size of this, and control it.
And control a relay, and you can make the relays kind of as big as you want. We could, and then somebody else suggested, maybe use MOSFETs instead of relays because solid state. I don't know if we need to be that precise.
SCRs are something that come into play. The problem with SCRs is that they are extremely expensive. They have not come down in price in the last 30 years in terms of what you're doing. When you're moving the higher voltage, now moving 24 volts DC, not a problem. Moving 120 volts AC, not a problem. But if you start moving 200 or 300 volts, what's your amp? What's the amps on your welder? 240, you know. And so when you strike an arc, that's what happens when that much electricity is dissipated over that short distance and forms the arc. It liquefies the metal. Well, that's the same. That energy is the same.
Yeah.
We have to control it. And that's why I was saying one of the things that we use in starting large motors and power plants and stuff like this is called a reduced voltage starter. And what that does is it's a series of coils that says, okay, we're going to start this motor up with 25% of power. And when it reaches a certain point, we switch and give it 50% of power. Then we switch and give it 75, and then we give it 100% of the power. And so that's what you're doing when you size your coils. Maybe you use a 200 turn coil and you're using something on the order of 100 volts.
Now, is that how big the coil is going to be? Our coils?
It won't be very big. It won't be very big. You'll be surprised.
Where does the coil sit? So you've got your plunger, right?
Mm-hmm.
Or your piston, and where does the coil sit in relation to
the coils being stationary? They're going to be wrapped around the outside of the pipe. The plunger is inside the pipe. Okay, so that as soon as the coils go, you do this. Now you got another thing you have to think of. If you get the plunger up to say 25 or 30 miles an hour, you got to stop it.
Yes, you do.
You don't want it shooting out. So you're going to need something on the other end that is stopping that much energy, or we might use something like the eddy current braking system to just let it slow down to the end. And then when the car comes back to the same starting point and it coasts up to this, then it's going to go against the eddy current drag. And if you put a load on those coils, that will create eddy current drag and it'll just go right back to its starting point.
Mm-hmm. Well, that'd be cool. All right. So, okay. All right. That's really interesting. We're going to, can I get a drawing of, I mean, like not right this minute, but like,
yeah,
if you tell me the stuff to do, I'll go do the stuff. It sounds like, and another question, certainly a question, you know, I'm gonna be wanting to answer for Liz as we get into this project. It doesn't sound super duper expensive so far. Am I right? Because we're talking about like copper wire and some.
Yeah, 10 pounds of the copper wire. I buy it by the coil from MWS Wire, and it's like $130 or $40. Depending on the gauge of the wire, if you're in the normal range of gauge of wires all the way up, you just get less of it because the coil size is the same. It's about this big around and this thick, and you just use the wire. So I look at it about $120 for 10 pounds of copper wire.
Okay.
Choose. And
how much copper wire do you figure it's going to take to make a coil?
Well, each coil of wire, and I'll use their website and look and tell how many feet of wire I'm going to get. They estimate based on the weight and the diameter, how many turns how much wire you're going to get out of it. And then we just go through the formula of trying to figure it out. Even though I'm an electrical engineer and I loved math when I went through school, I also love tinkering, and I'm a lot like you. I love to do it. And so what I'm looking at is I think of it, I can build one and test it quicker than I can calculate what it would do. Now, if I had the $20,000 ComSol physics and I could type it in, it would still take me a day to build the model in ComSol physics to come back, and I can build it in 2 hours. So I'm like, which would you rather?
Yeah, just build it. Yeah, I guess you can unspool a coil if you needed to. You could just like make another one.
But what I would look at is seeing I would build it one at a time. I'd put the first coil in and we'll just pick a number and a size so that we're getting, and I've got the information where I can give you that directly off of the magnets. And so let's just say we want to keep it so that we're using as much of the flux as we can that's greater than 300 gals. All right. Below that, it's such a diminishing return, it's not worth trying to capture that. So we just measure from the surface of the magnet where we get to the 300 gals, and that's as big as we need to make it. So it may be a 1-inch thick coil, and so we just spool it up at 1 inch thick, put it in a drill press, and 2 minutes later, you got you a coil of wire that's just exactly what you're looking for. And put the magnet inside and then hit the power. Keep in mind in electromagnetics, if you need more power, you just double the voltage. Okay, so you test 24 volts, and if 24 volts, gets you something and it moves and does pretty good, and you think, okay, this is pretty good, but I'd love to go faster. Try it with 36, then try it with 24. And I mean, try it with 48, and you step up the voltage within reason. Now, obviously, you don't want to go to 800 volts because that's when you can create, that's when you got a super arc welder that you're trying to harness. But you do it and say, okay, well, I got pretty good here. Now let me install that light sensor and set my next coil here, and we'll see how much power I need. And you may just need 2 coils. And then you've got the sensor, and then it just kicks it in because, like I say, the more I think about this, you're on something that's going to take very little energy. I mean, a 5-year-old can take your cart and give you a push and get you up to 7 or 8 miles an hour. So you're not talking about needing a big thruster to do a vertical launch on a 200-pound rocket. You're just not doing that.
Yeah. Okay, dig it. All right, so let's move to the other end of the ride now, because I don't want to burn up all of your time here. Now we do all of what you just said. We go up, we go over, we go down, and we're rolling back to the other end of the thing. How do we stop?
Okay. The eddy current drag is a really good effect, and you can go against copper or you can go against aluminum. Copper gives a greater braking effect, but at this point you may also want to consider the ride experience. When you're doing something that's a ride and you've got a person on it, stopping them as abruptly as the copper might do it might give them a sense of uneasiness, like it's about to throw them off of the seat. They're sitting in it, everything's been a cool ride, they're all excited, and all of a sudden it's like somebody just, like they hit a tree and it's throwing them forward.
Yeah. But yeah, think there's a ride down south in Southern California, Accelerator, and the stop on that one, it's like boom, it like pulls you. It goes from 0 to 85 miles an hour in 2.8 seconds, which is awesome.
That
right?
is throwing you through the front.
It is significantly more exciting than a Tesla Model 3 I discovered the other day. I reminded myself, but when it stops, it's like, ugh, it like you are pulled into your seat. And there's going to be some of that, but I do like the idea of it like being like smooth and not just.
And what you could do is use aluminum instead of the copper, because it doesn't generate as strong of an effect, but it still slows it down. And so what you may have is down the sides. We've got 2 ways of looking at this. One is we could have a set of magnets underneath the cart. You could have something that's off to the side. And you have 2 options. You can either install the magnets permanently on the sides and put the aluminum on the side of your cart, which is probably the best thing to do. Or you could put the magnets on the outside and then mount the aluminum on the outside. One of the 2 is going to be moving and one's going to be locked in place. Right. Keep in mind, it'll have to be bolted down pretty good, because it is going to dissipate the energy, the kinetic energy, through its installed structure. So it has to be firmly attached to something that's firmly attached to the ground and is not going to move. Right. Because you don't want somebody to come in and be slowing them down, and it's creating that bending moment around wherever its attachment point is and causes it to break free.
So it has to be super, super. How thick is what I've been thinking about? I've been thinking about it because, I'm like, I don't know if you know this, George, but neodymium magnets can get expensive. I don't know.
Because the Chinese run the price up by factors of 2 and 3 just randomly when they want to.
Yeah. So what I was thinking is like, okay, so if we wanted to, it seems to be like the least expensive way to do it, right? So good, fast, cheap, pick 2. I think that the cheapest way to do it, and correct me if I'm wrong because I'm just guessing, is if we mount the neo magnets on the cart, and then we have a series of fins coming up out of the track or plates, depending on how we manage it. Is that going to be like the best way to get the most out of our neodymium budget?
My thoughts are.
See, you hate it already. You do not like it. I could tell.
Well, here's the thing I'm looking at. If you start moving these magnets around, there's the chance that somebody could have a zipper on a coat and it sticks to the magnet, and then it causes it to catch as it goes around a curve or something like that. The fact that you have strong magnets would have to be significantly away from being able to interfere with anything else. If they picked up a nail, if they picked up a screw, anything, they can affect your ride. But if they're stationary in a fixed location that you're in control of, then you don't have to worry about that. And so putting the aluminum on the side of your cart, just 2 little strips of aluminum, 6 or 8 inches long, and then just have 2 or 3 magnets on each side, you're going to get all the braking effect that you need. And then, of course, you could have the secondary brake might be a spring that it runs into where it just pops into a spring, but you've already dropped 70 or 80% of the kinetic energy before you have something. You could literally get to the point you could just put your hand out and stop it at that point.
Yeah. Okay. So, because what I'm thinking about is, I'm thinking about a couple of things in terms of just like eddy current braking. One of the great joys of Accelerator, King to Ka, Top Thrill, Dragster, those 3 roller coasters in particular, is they generate just enough power to get you very up in the top, and when you get to the right at the top of the hi-hat, you almost stop. And the joy, the great luck is if you get to be on the cart when there's a rollback, because like you almost make it and then it rolls back. And this is like every coaster enthusiast's dream is like, oh my God, I want to be on King to Ka for a rollback. So, and then if there's a rollback, and those are catapults. They use hydraulic catapults to launch. Yeah. And so what happens is there's a set of aluminum fins, and there are magnets underneath the cart, I believe, on this one. There's a set of fins that go down before the cart launches, and then it launches. And then as soon as the cart passes, those fins come back up, and they're spring loaded, so they fail to the up position. And then when it comes back down, that's where the eddy current, that's the safety. And so if we mount fins on I'm wondering how we might manage something like that, because if it does roll back, we don't want the thing to come back and slam into the piston or do any of that ugly stuff and people on board. So stopping it coming back and stopping it at the end of the ride, those are the 2 I'm looking out there, because that's where it's all going to happen. Stopping it coming back and stopping it at as in the event of a rollback, that would be freaking awesome. And so that's the rollback prevention is a
I'll think about some more, because I had a second option I was going to mention on the let me see if I can use a couple of things here. I was looking at this as an option. Okay. If we had a magnet coil, say here, a copper coil here, and on this was where the magnet was mounted, and we energize this coil and it pushes this. Okay, we can take advantage of mechanical leverage on your launching to where now it doesn't have a long stroke, but this does. And so this may give the cart a 2-foot push. And if we could get enough power out of one coil by using the mechanical leverage that you get here, you just push it and now it takes off and goes. So you would use the same thing when it comes back in. The thing would be left like this. So as it hits, if you've got a load on this coil and the magnet moves towards it, it is going to generate electricity, and it'll generate a working resistance against it. And at the same time, it loads itself back up.
Okay, and then so it's spring loaded and it fails to the open position. So then when the cart comes back, it'll go whoop, and it'll stop it like that. And then then you just, when you're figuring out how much energy you need in your coil and capacitor system and all that stuff, you just figure, oh, we're going to need to push the cart and spring that spring.
If I'm looking at that coil and the amount of power you get in that initial like this gives you a slower takeoff than it would if you were getting it from this point here. So I was looking at 2 designs. One is the sequenced coils, which would give you more of a rocket ship type takeoff, or Model 3 type takeoff, where you just feel it really push you back over a distance. And the other is it mechanically accomplishes the same thing, but it's using leverage. And you're getting much shorter stroke that you have to worry with. You don't have a second set of coils. You just have one set of coils that hits it one time and it bumps you out there.
So your launch there is going to be much more abrupt.
Yes.
With the we don't want to say violent, but abrupt. It's going to it'll be like getting punched in the
It's going to be like hitting the gas hard on a Model 3. Whoa!
Yeah, and that's cool. And everybody that I've ever done that with, they love it, right? You know, especially kids, right? They're just like, whoa. But okay, so now, so kids. Here's another thing, and I'm going back a little bit to the well, I'm straight back to the launch thing, because we're going to have kids, and then we're going to have like John Elliott, who's a commercial electrician. And so it's like awesome that I've got like real, you know, we do have adults in the room
Yeah.
for this. Not me, but in the room. And so, but we're going to have like a 60-pound kid who's going to ride this ride. And then we're going to have me and John, and, you know, me and John, we're like, you know.
Now you handle some of that in the thickness of the foam that you put in the seat.
Right. Okay.
You can handle that, absorbing it with that. It's kind of like my first flight that I ever got to as a company I worked at. They sent a bunch of us up to a trade show, and we flew in a Learjet. And I sit down in this Learjet this is back in the 70s, and the seats are like this thick in foam. And I'm like, why in the world would you have this thick of foam? The plane takes off at a 45-degree vertical ascent, and the guy is kicking it as we're rapidly approaching 550 miles an hour, and I'm buried all the way back. And I mean, it's an effort to try and lean forward when he's taking off. And I said, now I know why you got the thick foam seats, is it buries you in the seats. The same thing here. If you've got a good takeoff, you just put a little extra cushion in it. Somebody that's 200 pounds is going to squash the cushion. Somebody that's 60 is not. And so, but the force of takeoff will give them just a little bit of that absorbance. It'll absorb that energy for them as they're starting to take off.
Okay, man, I'm trying to think of, and so again, going back to like the plunger, at over what distance are you thinking we'll achieve? Pardon me?
18 to 24 inch stroke is what I'd be looking at.
So over the course of 18 to 24 inches, we're going to go from 0 to 21 miles an hour.
Or faster. You'll be able to control it. If you do it right with the right electronics controller, and this is the way I visualize it. If you take this to the next step, what you could do is you could have it adjust the voltage based on the person. So if you put a 60-pound kid in there, it may hit 36 volts. If you put a 200-pounder, it may use 48 volts, or it may use 60 volts. But you're stepping up in voltage as you have a need for it. And so therefore, everybody has the same experience regardless of their weight, but the system just has a little sensor and says, okay, this is 60 pounds, and I adjust the voltage output to match what I need so that the 60-pound person moves with the same experience as somebody that's 200.
Right. See, that would be really, really cool. And that way everybody has the same experience. You don't disappoint the grown-ups, and you don't horrify the kids. Right?
That's it.
And so, wow, that's really, really, really cool. Okay. Tell me one more thing, George. I know you've got like adult responsibilities a little bit, probably not, I'm guessing not too much, but a little bit.
For math and science.
Yeah, I think we may have been like separated at birth. But so here's the next thing. What do I need to where I could maybe start playing with eddy current braking stuff? I mean, what are some of the bits and pieces that I should get so that I can, because one of the things I want to do in my next video, I want to make a coil. So I want to like start goofing around with that. So I need a shopping list for my coil, and then also a shopping list for just goofing around with eddy current breaker. Like, what size of magnets are we going to be bolting to the system here? Do you have that in mind?
Something in the 2-inch square by 1-inch thick. You just get they're very common. They are magnets. They're sort of like the middle line, getting smaller. You've got, if you figure it from a manufacturing standpoint, the smaller you make the magnets, they make a big magnet and slice it down. So the smaller the magnet, the greater the waste in making it to its final size because of the cutting. All right. Nice. So you have the price is going to go up on both sides of like a 2-inch cube. And so somewhere in that 2-inch cube gets us the best. But the difference between a 2x2x1 and a 2-inch cube is not going to be that much in terms of power output for what we're working on. And you always know you can go to a 2-inch cube if the 2x2x1 doesn't get you exactly what you're looking for. Another thing you have to keep in mind, I saw in one of your videos, you're wearing these wonderful leather gloves. It's exactly what I wear as my leather welding gloves. And the leather welding gloves are not going to stop the magnets from slamming together. They're not going to stop magnets from breaking. What it does is it allows you to get your hand out so that you can separate them later.
I was thinking about that. You could break your finger like
these are in the body part crushing category of our magnets. And so that may, and I've been using that term for 20 years. Body part crushing means exactly what it says. You get a body part between two of these magnets, it will get crushed. And so having the glove means you live to fight another day.
Right. It's going to hurt like hell.
I will tell you this. This is another little safety tip when you're working with large magnets. If you got the gloves on, if you get two that snap together accidentally right here, push your hand further in, and then you can pull the other one away because you've increased the gap between them. If you start pulling, they're getting closer together. And every time you try to pull it out, I picture it's kind of like the comic book hero, the Hulk. And the Incredible Hulk says the longer he fights, the stronger he gets. Well, the closer you let the magnets get, the stronger they get. And so they just start flattening out your skin and make it very difficult to get your hand out. So
yeah, this is where I we talked about this before. I went to Louisiana Tech University, which is right near you, which either makes us friends or enemies. I'm not sure. But I learned to fly airplanes there, and one of the main lessons you learn, I think everybody should learn to fly. One of the main lessons I learned is that very small actions can have very big consequences. And so I'm really good at being careful, and I'm really good at being safe. And so this is important information when you're dealing with these super strong magnets, is like nothing you do is trivial when you're building with those little things. And so we'll have to, how do we attach? And you're thinking of a magnet just passing over. You're not thinking about like two magnets and a fin going in between them. Are you? Just a magnet mounted like flat on the bottom of the cart, and it just passes over, much like your skateboard video. Exactly. Just awesome. Okay, how thick is the aluminum? How thick is our aluminum track?
I would go with a 1/2 to 1 inch. And sometimes you can find this at a scrapyard. We sell, ours are square blocks, mostly for demonstration, 1 foot square by 1 inch thick. But you may be able to go to a scrapyard and find it. I've got a bunch of scrap aluminum that I found at a place, because you get cut-offs from a steel supply company and go, and they'll have a scrap bin where they will have taken something and cut a 6-inch strip off. Well, if you get a 6-inch strip of 1 inch thick that's 2 feet long, that's perfect. You could also use 7 inches. You could also use 10 inches. If you can find a good piece that's scrap, that's a good way to get it.
Yeah, and that's another cool thing, as I understand it, about eddy current, is once it starts to slow down, the currents really don't matter anymore. And so you could have like a 2 foot, 3 foot strip of aluminum, and if it's going really fast, it'll slow it down. And if it slows down in the first 6 inches, it'll just kind of dribble off the end. No worries.
And that works extremely well. On the safety thing, I always, I'll give you this warning on working with large magnets like we're going to need to work with. What you want to do is keep in mind, the magnets are faster than you can imagine they are, and they are stronger than you can imagine they are. And so no matter what you do, the thing that I do as my extra safety when I'm working with the large magnets, I take my cell phone off. Not that I'm worried about the cell phone causing any problems. I take my watch off, and I tell everybody in this shop, do not talk to me. At this moment in time, there's not a phone call that's important enough for me to do it. When I finish and I get to a safety spot where I know where everything is and I've got everything where it needs to be again, then I can take care of calls. Because where most people have their accidents is, let's just say you get a magnet in your hand and you're fixing to do something, you know what you're fixing to do, and you're concentrating on this, and you get a call and you look at it and say, oh, darn, I need to take this call. And so you start doing that, and in just a split second, you've moved the magnet, and now that pair of pliers or that knife or that screwdriver you got there is instantly flying to you. And so you can't afford, when you're working with big magnets and strong magnets, you can't afford a momentary lapse of concentration.
Okay.
And so that's
really, really important.
Because when I get a chance to meet you, I want you to have all 10 fingers.
Yes, please. That's okay. Tell me one more thing about magnets. How do I fasten the magnet to my cart? How do I don't just go clunk and just like let it sit there. It's got to be.
Probably with your skill in welding and cutting and so forth, what I would probably do is get something like a piece. If the magnet's 2 inches in diameter, it'll fit inside of a 2-inch piece of pipe, and just get either a little coupling or get a piece of pipe that you just use a bandsaw or something and cut off a 1 inch wide piece of pipe and just let the magnet go inside of it. You can use something like a liquid nail or something like that, that you just want some sort of adhesive that's going to do two things. One is it goes in, it's going to act as an absorbing shock so that it doesn't instantly hit. It's got a little bit of hydraulic fluid stuff it's got to squeeze out. And then once it finishes pulling its way in, it's going to stop, and then you wipe off the excess and it'll stay there.
Okay, so we don't have to worry about like attached because you know it's neodymium. Okay, all right. So what I'm imagining is like building a little like 2-inch wall out of just like
you can have screws in the corners of it that bolts it to your carriage.
Yeah. Okay. Cool. And then when it passes over the aluminum, we want to get within like what, 1/8 of an inch, 1/4 of an inch, closer the better. What if I put, here's another, I'm sorry, George, I've got all of these like relentlessly stupid questions because this has been cooking in my head. I've been excited about this conversation for weeks. Okay. So what if I take to manage, we don't, as soon as it touches, I'm guessing your eddy current thing is over, right? Game over if it touches?
No, it'll slide. It's strongest when it's in contact with it. The thing that you run into is the possibility of damaging the magnets. The magnets are very brittle. And so if they made contact with aluminum plate too hard, too often, then there's a chance that you might crack a magnet. That if it's mounted inside of a steel frame and that steel piece of pipe that I mentioned, it isn't going anywhere. So the fact that it's a crack doesn't affect.
So is there something I was thinking of like I was thinking of like maybe 3D printing some very thin cover.
Yeah.
So that it manages the distance between those two things so that it's the same distance every time, and then maybe also we protect the magnet a little bit of friction. That 3D printed thing maybe needs to get replaced every once in a while, but is that like
another suggestion is you might want to use as your cover plate something like 1/8 of an inch Teflon, PTFE. That stuff is the slipperiest stuff around, and it's very, very tough. And so it's a very hard, tough plastic, so it'll last a long time, and it won't slow things down.
And it won't slow things. 1/8 inch Teflon. Okay, cool. Because that way we can manage the thing. We can even have the aluminum fit plate a little bit. That might even be like a little bit spring loaded or something, and maybe just a tad bowed at the beginning. So when the cart comes along, the fin, it meets it reliably and predictably without destroying the magnet.
And if you pictured it so that maybe you tilted the aluminum plate so that at the initial point, it may be 1 inch apart. It's going to get some drag, but not much. But it tapers to where it's 1/8 of an inch apart, and then have another piece that's 1/8 of an inch apart that's flat. But this first part would give you a more gradual braking effect, and then it glides right on top of where it's just, you may even have to push somebody off of the last 6 inches of it. And if that's a problem, you just make it 6 inches shorter. And so.
Oh, okay. Yeah, because is there a point where it'll just like lock it down? Because a neomagnet's not going to stick to aluminum, is it?
The eddy current effect velocity. So as you go faster, the harder the effect is going to be. As it slows down, it's just going to be like pushing it through water. It's what it'll be. As the cart will come to a near stop, and then if you're still over the aluminum, somebody may have to push them that last little bit just to get them off, because they will come to a stop over it.
Yeah. Well, and that's what we want. We want to, that's what we want. That's okay, George. There's like so much. I'm gonna reach out to you right after this. I'm gonna get my little shopping list. I'm gonna get some toys so that I can do some experiments and show some people the amazing joy of magnetism and what all is possible. And and like I'm so grateful for the time, guys. Check out youtube.com/supermagnetman. Go check out what George has been up to for, golly, how many years now have you been doing this?
I started with my first YouTube video in 2007. And a lot of people that are getting into YouTube in the last couple of years have made comments on my video. You've been making videos since 2007 and you're still answering comments? Yes.
Yeah, well, that's how you tell. That is like proof positive that you absolutely love what you do. No doubt you've got the best job ever, dude.
I do.
George, again, thank you so much. Thank you so much for all the fun. And everybody, we're gonna keep going with this crazy magnetic thing. Thank you for helping me bring physics, family, and fun to kids everywhere. I'm Will Pemble. That is George Mizzell.
Thank
We'll
you.
See you soon.